Alright, so in this video we're just going to do a little overview of programming. So we'll first discuss the parts of a computer, look at the structure of a software program, talk about generations of programming languages, programming constructs, types of execution, programming paradigms, terminology, and then lastly we'll introduce Node-RED. So parts of a computer. Of course, the standard parts of a computer, we have input devices, which are keyboards, mouse, and the network connection. And then for the industrial computers or PLCs, we also have sensors, switches, which are ways to send inputs to the controller. Output devices, the standard output devices are things like a monitor, possibly a printer, your speaker, and of course the network. So a network is both an input device and an output device. We can send information out or receive information. And for the industrial controller, of course, we have actuators, motors, relays, lights, speakers, things like that. Then of course we have inside the computer, we have actually the processor or microprocessor, the controller that is actually going to execute programs. We have memory that is going to hold program instructions and data as it's being executed. And then we have storage, which is going to be where we're going to store the data and programs for long-term storage. So memory is a short-term storage, and just holding it there, waiting for it to be executed. Usually this is what we call dynamic memory, meaning that it will be lost if we lose power. Where storage refers to we're storing it what used to be in a hard drive, which was an actual magnetic rotating disk, but now we have what we call solid state drives, which are actually more of memory, but they're flash ROM memory that will remember the data even without power. All right, so when we talk about a program and we talk about running this program on a computer, on a processor, it has to actually be in binary form. All right, so binary form or machine language is unique to each processor. I guess the word processor got kind of cut off there. Okay, so if you have an Intel processor, then it has its own language. If you have an ARM processor, it has its own language. If you have like a Mac computer, it has its own language. If you have a PLC, it's got its own machine language. And so that's why you can't just like take one program from one type of computer and run it on the other, because it needs to be in this machine language, which is just binary or ones and zeros. And so when you're trying to do something, like in this case, the idea is I want to add two numbers together. And so to do that, I would have to have an instruction which would move the number. Say in this case, I'm going to add 10 to 3. So I'm going to add 10 and 3 together. So my answer, of course, should be 13. Don't know why I chose that lucky number, but that's what I chose here. So I have 16. Well, this is for a 16-bit processor, and so I have the instruction. And so as I kind of highlighted here that there's some differences here. So this 16-bit instruction might be, this one here might be to move the data from that long-term storage into RAM, because you can't process, the processor can't do anything with what's in long-term memory. It needs to get it into a local memory storage, RAM memory, and to do something with it. So this might be the instruction to move it from that long-term storage into this location where it can actually do something with it. And so it's going to move the one value, which happens to be 10. This is the value 10 in binary. And then it's going to move another value, which in this case is in another location, and it's going to move it, and then it's going to add those two together. So it gets them into place into two registers within the processor itself. So the processor itself actually has what they call registers, which are short-term memory. So these instructions are moving it actually from the normal RAM inside of the processor to make it to make these available into location A and B. And then it's going to and then the third instruction there is going to say, oh, I'm going to add these two together. Now typically what happens when you do an add instruction, it automatically puts it into a result, which I'm calling C here, location C. So when you take what's in A and you add it to what's in B, then the result it automatically goes into this local inside the processor itself location called C. And then we need to move that C back out into the ordinary memory or RAM. So this is what the machine language might look like, but again, this would be only for one type of processor, whether it's a ARM processor that maybe a phone or a BeagleBone uses, or it might be for a Windows Intel 7 processor. Of course, that's a 64-bit, but the point is that it would be different for each type of processor. All right, so in the early days of programming computers, you had to write them in machine language. So you had to use this binary representation. And then they did this huge advance. They went to the second generation where they used something called assembly language. So in assembly language, it would look like this: move A. And then so you're moving the value 10 into A. Then you're moving the value 3 into B. Then you're adding A and B, which again automatically puts it in C. And then you're saying take this result and store it in some physical memory location out in the general RAM. Okay, so this is the assembly language of the 1G language that I just went over up here. Okay, and the problem with either one of these is they were tied to the machine. So if you wanted to then move it over from a Mac to a Windows to a cell phone, you would have to rewrite all of this using the appropriate language. So even with assembly language, in general, each assembler tool had its own little nicknames here. So move A, move B, add A, B. These might be completely different on an Intel compared to an ARM processor. So the idea then was to come up with what they call high-level or processor-independent programming languages. And the first of these was actually C. And so the C programming language was, at least originally, intended to be processor independent. So you could write it in C, and then you would use what's called a compiler, which would compile it down into the machine language for each thing. So you just needed a compiler that would convert the C into the machine language based on which machine you're actually trying to compile it to and run it on. The problem with that was that they set these standards for C, and then people added extra features that only worked on certain computers, which made it dependent again on the type of machine again. Okay, but nowadays we're getting more into what they call fourth generation and fifth generation, which actually makes it much more generic, where you can use more English language type skills or even graphical skills. Okay. All right. So the constructs of a programming language, it doesn't matter what language you're going to use, you have to be able to, number one, read input data, and then of course do calculations and then be able to output that data somewhere. If you can't get the data in and you can't output it, what's the point? Okay, so then you have to be able to perform whatever calculations, execute various logic. So the difference here is calculations is a lot of times referring to adding, multiplying, dividing, things like that, where logic is looking at more of instructions like the AI stuff we talked about with like just if statements. So if statements aren't necessarily AI, but if this is true, then add them together. Or as we talked about with the tank system, if the sensor is saying the tank is full, then shut off the actuator. So you have to have this logic. Okay, this is true or false. And then, of course, you need to perform multiple iterations, right? One of the big things about computers is the fact that it can repeat, repeat, repeat. All right, so when we talk about executing this program, again, the program always has to be in machine language to be executed. But the question then becomes, when do we convert it from more of a graphical base or text-based version that we can easily read into the ones and zeros that the computer actually needs? And so there's two ways of doing this. There's one thing is what you say a compiled language. The idea of the compiled language is you compile it into the machine language, and then that is your program, and then you can execute it whenever you want. The other way is to do what they call interpret it. Okay, so compiling it, I guess, is just referring to converting it from a language that we can more easily understand than the ones and zeros into the ones and zeros. But we can do that immediately, as right before it gets executed, which is called an interpreter. So the idea is you can have a converter tool or compiler that's going to convert it from the general text into the machine language just before it's executed, or you can compile it ahead of time. So if you compile it ahead of time, the advantage there is now it's already machine language, it's ready to go. And so in general, pre-compiled programs are going to execute much faster than ones that you have to convert every single time, because you first have to convert it into the machine language, then you execute it, then you forgot what it was, so the next time you run the same program, you're going to have to convert it or interpret it again. All right, so the downside of interpreting it is that you have to interpret it every time, and that's an extra step which really slows down the execution. Okay. Java, when Java came out, it was kind of a combination between it. What the idea was is that you could compile it into what they called bytecode, which wasn't quite machine language, but it was closer to machine language. But the idea was then you could have a Java interpreter that would interpret it for whichever hardware. So the idea of Java was it was supposed to make it independent. So it would only, you could write the program and then run it on anything once you had this bytecode interpreter. So you would have to have a interpreter for each type of machine you were running it on. So it's kind of in between the two. It does a pre-compile into bytecode, but you still have to convert the bytecode to machine language when you run it. All right. When we're talking about errors and programs, there's two types of errors. One type is a syntax error. Syntax errors are caused by the program not being written out properly. So if you think about like English, right, at the end of a statement you have a period, but if it's a question at the end of it you have to have a question mark. And so, there's a difference there. Those types of errors would refer to kind of like a syntax error. You're missing a comma or you've got a misspelling, things like that. And so when you do a pre-compiled program, one of the things that you're doing as you're going through the compilation is you're checking for syntax errors. And once you get it fully compiled, you have no syntax errors in the program because it wouldn't compile if there's syntax errors. Where if you're running an interpreted program, you've got to check for those syntax errors again every single time, and again, so that adds extra time into the interpreted. So this is why interpreted programs typically run way slower than a pre-compiled program. However, along with syntax errors, we also have what we call logic errors. Logic errors are errors in the program that have nothing to do with like misspellings or missed punctuation, instructions like that, but they're due to an error in the program that is either because the programmer's logic was flawed when they created it, or it could simply be because the programmer was expecting certain type of information or data to be in a memory location, and for some reason it's not there, or the data that's there is not what the programmer was expecting would be there. And either way, it causes the program to either totally crash and quit, or sometimes it seems to like go in an infinite loop and it'll never quit, or sometimes it just does weird things and you don't know why. And again, it's because the data that is within the program isn't what was expected, and so and it wasn't planned for, and there wasn't any check to make sure that it was correct, and so these weird things are happening. All right, so when we try to store a program, we can store it in a few different places. We could store it into flash memory that is like burnt into uh, the computer. So one of the most common these is the what they call the BIOS, or the boot up program, a computer. These are stored within the computer. They come from the factory that way. You can usually upgrade it, but you can't run the computer without it, because this firmware usually tells it like how to talk to the hard drive or to the solid state drive or to a USB drive to actually download or to read any other data. So without this, you basically have a brick. All right. So software, the programs that we would create and run to run our manufacturing lines or whatever, to talk to our sensors and our actuators, we would store either on a hard drive or some sort of a long-term storage device in there. And that would be our software. Like I say, those are like programs that we created or downloaded or got from somebody else. When we want to actually run our software, as I sort of mentioned before, we have to load into that general dynamic memory, which we usually refer to as RAM, as read. RAM stands for random access memory, meaning that it can go out and it can get the data from A or B in whatever order it wants. Okay, where typically the hard drive or SSD type of storage, it's kind of a sequential data, so you have to get it in order, and so the program needs to get it into the random access location so it can work and go back and forth to different locations to get the data as it needs. All right. So as there's a couple of paradigms when you're talking about how to create a program or how to structure a program. So you can kind of think of this as maybe a philosophy about how the program is going to be built or how it's going to run. So one paradigm is what they refer to as imperative, which means that the programmer gives the program instructions and it lays out the procedure. The other one is the programmer lays out the results, and then the program kind of comes out. So that's kind of more of an AI sort of thing where you say, this is kind of what I'm looking for, and then I want you to give me those results. So that's called declarative. Within there, we have minor paradigms, which are procedural, which means we're going to lay out each step, or functional. Functional refers to tasks that can be completed in groups of things. So it's like, okay, well, you go over here and you do this, and you go over here and you do this, and then later on somewhere we'll kind of bring them together. Okay, so we have function. Usually these are kind of referred to as function calls. And then we have something called object-oriented. And the difference between functional and object-oriented is basically that the data is encapsulated within the functions. So it's kind of a functional sort of thing where you have this function that's going to go do this, but the data and the functions are tied together into one object. All right, some various terminology here. We have a variable. A variable is simply a name of a memory location. Sometimes we also call this array if we have lots of like data stored together. Data types. You can have different types of data. You can have an integer. An integer is a number without decimal points. So, 1, 2, 587, those are all integers. There's no decimal point. A floating point is a number with a decimal point. So if you think about, say, the number pi, 3.14159, or 0.7, anything with a decimal point needs to be stored as what they call a float value. And then a string would be a string of words or sentences, anything like that. So if you look at this slide, pretty much everything on this slide is just strings. Index. An index is the value into an array. So if you have a lot of like data, then you can select which bit of that data you want by using an index. Scope. The scope refers to where that variable is accessible at. And so you can have, like if I say we have an object, and with the object-oriented data, the data and the functions are together. So those functions can read that data and manipulate that data, and they're all combined there. But other functions or other objects can't get that data out of that object, okay? Or if they do, they can only do it by going through built-in functions within that object. They can kind of ask that object to run a specific function to try to pull that data out. They can't just go in and yank it out themselves. And so that's the scope. So you have this object, object 1, object 2. You can't, they can't just go grab data between each other. That data is locked in those different objects. But if you have global data, now that data is sitting out here, and either one of those objects can go out and utilize this global data. Okay. RAM, I already kind of referred to RAM. RAM is this dynamic memory where the program has to be held as it's actually being executed. And then shared memory is a special type of random access memory that can be shared between different programs that are running, they got to be running on the same same processor, but it can share memory. Typically, what happens with a program is when you load up a program, the operating system or whatever says, okay, well, I'm going to give you this area of RAM to store your data in and manipulate your data in this area. And then you have some other program that's running and it's got its own memory location. And, for safety reasons and stuff, these two different programs aren't allowed to go in. And, they're totally separate programs. Like if you think about your web browser, your Chrome web browser or your Edge web browser, it can't go into Microsoft Word and pull data out of Microsoft Word, that even though you're running them at the same time on the same computer. They're separate programs. They're not allowed to share their information. But through this shared memory, they can, if they're set up, it's a special, usually fairly small location of memory where the one can kind of put information down into that memory, and then the other one can come out and take that and then maybe replace it with something else to be passed back and forth. So it's kind of a way of passing information between two programs running on the exact same computer. And you could say, well, you can do that through a network connection, but the difference here is memory. This RAM, this dynamic memory on the computer is like 100 times faster than, say, any kind of network transfer. So it's very, very fast, but it takes special setup to get it to work. Both programs would have to be set up and correctly for that to happen. All right, so if we're talking about creating a program, there's something they refer to a lot of times as an IDE, which is an integrated development environment. So this environment, it has like an editor so we can create the program, and then it has a compiler or an interpreter tool to actually convert it into the machine language for us. So we already kind of talked about the compiler. The compiler is compiling it into the machine language. Again, we could do that either right before we execute it, which is interpreted, or we can pre-compile it. But we have to take that our general program in human text or graphical form and convert that into the machine language for the computer. The other thing the IDE will typically do for us, it will give us a set of common libraries. Libraries are sets of functions or instructions that we are going to perform all the time. So like if you wanted to, say, send something out to a printer, right? You don't want to have to rebuild the printer driver every time you wanted to print something out. So they have print functions that are built in into these libraries, and then you can make use of them. Source code is the raw code created in a high-level language that I can say usually it's in a human-readable form, so we can look at it and understand it, but it's not in machine language, so technically it can't be executed. All right, for this class, we're going to be using Node-RED quite a bit. Node-RED is basically a fifth generation integrated development environment for creating programs. So it has a large graphical nature where you have these things called nodes. You can grab a node and drag it onto into the program area, and then you can connect those together very easily. Okay. It does allow lower level coding as you need to, so you can get down and do basically what results as JavaScript. So to access this, you have to, of course, have it installed. One of the cool things about Node-RED is it will run on virtually any type of computer. It'll run on Windows, it'll run on a Mac, and of course it's going to run on our BeagleBones, which is where we're going to use it the most. Okay. Now it uses this concept of flows. So basically a flow is a set of instructions where you have, like, in general, you're going to have inputs, and then you're going to process those inputs and generate outputs. And so the data is going to flow kind of left to right, where you have your input and then you run it through various functions, and then you have outputs which are actually doing some sort of actuation. So that's the end of this video.